In the last few lectures, if you recall, we have been talking about the design of different kinds of adders and subtractors, stuff like that, which are very important for the design of more complex systems. So, you know, addition is a very integral part of most computations and systems that we design. So, in this lecture from today onwards, we shall be discussing some of the other basic building blocks that are available for designing functions, implementing functions and so on. So, today we shall be starting our discussion on general logic design. So, logic design is somewhat general in the sense that we are not talking about specific applications like addition or subtraction, but we shall be talking about some generalized building blocks which we can use to implement any arbitrary function. Let us see what we plan to cover. So, as I had said that we shall be talking about some of the common functional blocks which we normally use in the design of digital systems. Now, specifically the kind of functional blocks that we shall be considering are multiplexer, which we have already seen earlier. See, earlier when we discussed about the CMOS switches, the transmission gates, we mentioned how we can very efficiently implement multiplexers using those transmission gates. So, we shall be revisiting multiplexers and what kind of applications and designs we can do using that. Then we shall be talking about something called demultiplexers and decoders, then encoders and comparators. Now, all these blocks are quite important in the design of more complex digital systems. So, for those of you who will be going into the design of complex systems, you will find that these modules will be used repeatedly in various scenarios. So, we start with our discussion on multiplexers, which are also called data selectors. Now, why do we use the term data selector for a multiplexer? Let us try to understand. If you recall, what is a multiplexer? A multiplexer is a block, if you think it as a black box, which has a number of inputs and one output. Depending on some select inputs, one of the input line is selected and it goes to the output. So, in a sense, we are selecting one of the several data inputs at a time. That is why this is also called a data selector. So, let us talk in a slightly general term. So, let us consider a multiplexer which has n data inputs. Let us call them as D0 up to Dn minus 1, and let us also have m number of select lines. So, we have a multiplexer as a box. So, in the input we have this D, the n number of lines, and then we have the select line S, and we have an output, single output F. This is how a multiplexer is. There is one output line F, and as we know the way a multiplexer works, depending on what we apply on the select line, one of the data inputs is selected and it goes to the output. So, if we consider this m bit select line as a binary number, if we consider the decimal equivalent. So, when S is 0, the first input D0 is selected, we will have F equal to D0, D0 will go to F. If S is 1, then D1 will be copied to F, F equal to D1. If S equal to 2, similarly D2 will be copied and so on. Now, usually there is a relationship between n and m. The number of select lines should be large enough so that any of the n inputs can be selected. So, this condition can be expressed as n equal to 2 to the power m, or alternatively we can write m equal to log to the base 2 of n. These two are equivalent, right. Now, because the number of inputs is 2 to the power m and there is a 1 output, we also refer to this kind of a multiplexer as a 2 to the power m to 1 multiplexer. Okay? Fine. So, this is how this multiplexer will look like. There are n inputs, there are m number of outputs S 0 up to S m minus 1, and there is a single output, as I have just said. Okay. This is how a multiplexer looks like. Now, let us talk about specific small size multiplexer for specific values of m and n, and let us see how we can design or implement such multiplexers. You recall earlier when we were discussing CMOS logic, we showed how to design a multiplexer using transmission gates, but here we shall be showing the designs using basic logic gates like AND, OR, NOT, NAND, NOR, etc. Okay? Let us see. Let us start with the simplest and smallest kind of multiplexer, which is 2 to 1 multiplexer. There are two inputs D 0 and D 1, there is one output. Because there are only two inputs, which is n equal to 2, we require m equal to 1, 2 to the power m equal to n. Okay. So, there will be a single select input. All right. Here I have shown an expression. Before coming to this, let us try to see how this multiplexer works. Let us try to construct the truth table. So, there are 3 select lines, 3 inputs S 0, let us show D 1 first, then D 0, then F is the output. So, there are 8 possibilities 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0 and 1 1 1. So, according to the definition of a multiplexer, if S 0 equal to 0, if S 0 equal to 0, then we should have F equal to D 0, D 0 will be selected. So, the first 4 rows show S 0 equal to 0. So, whatever is in D 0, that will go to F 0 1 0 1. Similarly, when S 0 equal to 1, then D 1 will be selected. So, the last 4 rows show this case when S 0 equal to 1. So, D 1 0 0 1 1, this will be selected. So, this is the truth table of the multiplexer. Now, if we construct a Carnot map, for example, and try to minimize this, let us see. On this side, let us show D 1 and D 0. So, this is 0 0, 0 1, 1 1 and 1 0, and in this side we show S 0, 0 and 1. The true min terms are 0 0 1, 0 0 1 here, 0 1 1, 0 1 1 here, then 1 1 0, 1 1 0 here and 1 1 1, 1 1 1. So, you see here the minimum set of cubes will be this and this. So, what does the first cube indicate? S 0 bar and D 0. You see in this expression S 0 bar and D 0, and the other cube is S 0 and 1 1 and 1 0 is D 1, S 0 D 1. So, you see after constructing truth table and minimization, we have arrived at this expression, but we could have arrived at this expression without going through all this minimization procedure, just by thinking about the functional description of a multiplexer. What is a multiplexer? If S0 is 0, we will get D0, if S0 is 1, we will get D1. So, how do we express it? If S0 is 0, which means S0 bar, we get D1, which is AND D0, we get D0 and D0, or if S0 is 1, which we write as S0, we get D1 and D1. So, we can write down this expression straight away without going through all this minimization, right. Okay. Let us move on. Let us talk about a larger multiplexer, a 4:1 multiplexer. For a 4:1 multiplexer, the number of inputs n is 4. Therefore, number of select lines m will be log to the base 2 of 4, which is 2. So, S0 and S1. So, in the same way, depending on the values of S0 and S1, one of the inputs will be selected. So, just following the principle I mentioned for 2:1 mux, we can straight away write down the sum of products expression for the output function. How do you write? From the functional behavior. If S0 S1 is 0 0, then we should get D0. We write it like this: S1 bar S0 bar indicates both are 0 0, then this will be 1 1 and D0. So, if S0 S1 are 0 0 and D0, then this f will be equal to D0, right. If it is 0 1, that means S1 is 0 bar and S0, then D1. If it is 1 0, that means S1 is 1, S0 is 0, then D2. When both of them are 1 on 1, then D3. Okay. Now, you see this is a 6 input function D0 to D3 and S0 to S1. So, if I construct a truth table in the normal way, there should be 2 to the power 6 or 64 rows in the table. The truth table would be too big to draw. So, again because of the functional characteristics of a multiplexer, we can show the truth table in a much compact way using some entries as don't cares. How do we do it? Let us see. Here we do it in this way. You see, first 2 rows of this truth table indicates the select line 0 0. So, you know when it is 0 0, then D0 will be selected. So, we apply D0 0, D0 1. So, the output will be F0 F1. Now, under this condition, the values of D1, D2, D3 are all don't cares. It is only D0 which will be copied to F. Similarly, when I apply 0 1, then D1 will be copied, the others will be don't cares. If I apply 1 0, D2 will be copied. If I apply 1 1, then D3 will be copied. So, you see we can very concisely express this truth table in only 8 rows. This is possible because of the nice functional behavior of a multiplexer, right. Okay. Let us now see how we can build multiplexers. Let us say we have smaller multiplexers available to you, and we shall be talking about how we can build larger multiplexers using these smaller multiplexers. Let us take a couple of examples. The first example we take is, suppose we have 2:1 multiplexers available to us, but we require a 4:1 mux. So, what is a 4:1 mux, you recall again? There will be 4 inputs D0, D1, D2 and D3. The output will be F, and there will be 2 select lines S0 and S1. Now, you see how we have designed this multiplexer network. We have used 3 multiplexers. In the first level, we are using 2 multiplexers, and both of them were using S0 as the select line, whereas for the next one we are using S1 as the select line. Let us try to see the different scenarios. Let us say S1 is 0. Suppose we have applied 0 and 0, what will happen? First is, let us look at the last multiplexer first. If S1 is 0, then the first input will be selected, this one. So, we need not have to see what this multiplexer is doing, because it is not being selected. The first multiplexer is being selected, and S0 is also 0. So, S0 0 means ultimately D0 gets selected. So, if it is S1 and S0, I am selecting D0. If it is 0 1, same way, if it is 0, this is selected, and if S0 is 1, then now D1 is selected. So, D1 will go out, D1. If I apply 1 0, if S1 is 1, then it is not this, but this line will get selected, and it is the lower multiplexer which will get selected, because S0 is 0 here. So, now this D2 gets selected and D2 will go out, D2, and if I finally apply 1 1, this S0 is also 1. So, now D3 will be selected. So, you see that it works perfectly as a 4 to 1 multiplexer. So, if I have only 2 to 1 multiplexers available to us, so we can very easily construct a 4 to 1 multiplexer. Let us take another example. Let us say we now want to have an 8 to 1 multiplexer, and we assume that we have smaller multiplexers available with us. Smaller means we have 4 to 1 multiplexers and also 2 to 1 multiplexers. You see, the network looks similar. We have used multiplexers in 2 levels, with 2 4 to 1 multiplexers in the first level, which are selected by S0 and S1, with the first 4 data inputs connected here, the last 4 data inputs connected here, the outputs of which are feeding to the second multiplexer, which is selected by S2. Let us try to understand the operation with respect to the truth table. This is the functional truth table I am showing with respect to the select lines. S2, S1, S0. If it is 0 0 0, then D0 is supposed to be selected, 0 0 1 D1, 0 1 0 D2, and so on, 1 1 1 D7. Let us look at it one by one. Let us consider the first scenario, where select lines are 0 0 0. If S2 is 0, this will be selected. If S1 S0 are both 0 0, then this one will be selected, which is D0. This is fine. Let us take another case. Let us say talk about this with this one, because S2 is again 0. So, again this is selected, but S1 S0 is 1 1. 1 1 means 3. This one will be selected, D3. So, it is D3, this is fine. Let us take another example. Let us consider this. Here S2 is 1, right? S2 is 1. So, this one will be selected, the second input, that means this multiplexer, and S1 S0 we have applied 1 0 or 2. 2 means 0 1 2, this one will be selected, which is D6. So, you see this works exactly like a 8 to 1 multiplexer. So, in this way, if you have any smaller multiplexers given to you and you are asked to design a larger multiplexers, you can systematically construct the multiplexer network like this. So, I have shown 2 small examples, you can think and work out larger examples similarly. Okay? Fine. Now, let us talk about how we can implement logic functions using multiplexers. First, let us see that if I have a 2 to power n to 1 multiplexer, we want to implement an n variable function. How do we do it? It is very simple. Here I am showing an example of a 3 variable function. So, I need a multiplexer with 8 inputs. And 3 select lines. So, what we are saying is that we shall be connecting the input variables to the select lines directly. So, we have A, B, C, we connect them like this A, B and C. So, what will happen if A, B, C is 0, 0, 0, the first line will be selected. If it is 0, 0, 1, the second line will be selected, 0, 1, 0, the third line will be selected and so on. So, what we do? We look at the output column of the truth table and simply copy this and apply it to the inputs 0, 1, 0, 0, 1, 1, 1 and 0. The output is f. So, you see the implementation of any function using multiplexer is very trivial, and the same multiplexer can be used to implement any arbitrary truth table if you just change this input 0 1 assignment. Basically, you are applying the truth table whatever it is to the input of the multiplexer, and the multiplexer implements the required function. This you can say is something like a programmable logic function generator. The input you change without any change in the circuit, circuit is the same, still that multiplexer. You only change that 0 1 pattern in the input, you get another truth table and that corresponding function gets implemented, right. So, it is very simple. Now, in this context, let me just ask you one thing, means one thing we did not mention possibly earlier. Let us suppose, let us remove this. Let us suppose we have an n variable function, you have an n variable function. So, my question is, how many distinct functions are possible? Functions are possible. Well, here we are raising this question because we are talking about programmability. Okay? Just by changing this input 0 1 pattern, I can change the function. I can go for one function to another. So, my question is, in 3 variables for example, total how many functions are possible? Let us think in this way. Think about this truth table. This is a 3 variable function for n equal to 3. So, I have my output specification here. This output column specifies the function. So, how many bits are there in the output? 8, there are 8 rows. How do you get 8? 2 to the power 3. Now, you consider this as an 8 bit number. So, how many possible 8 bit numbers can be there? Now, you have learnt about binary numbers. So, in 8 bits how many possibilities can be there? 2 to the power 8. So, the total possible number of these 8 bit vectors you can have will be 2 to the power 8, means 2 to the power 2 to the power 3. In general, for n variable it will be 2 to the power 2 to the power n, right. This is how you get the total number of functions that are possible in an n variable function. Like this here, for the multiplexer case also, for the same 3 means 8 to 1 multiplexer, you can implement so many functions, 2 to the power 8 or 256, this is 256 functions, because there are 256 kinds of truth tables you can generate by changing this 0 1 pattern, right. Okay. Now, let us try to improve upon this. For an n variable function, we are requiring 2 to the power n to 1 multiplexer. Now, what we are saying that we can do a little better. How? We are saying for an n variable function, let us use a smaller multiplexer. We can do with 2 to the power n minus 1 to 1 multiplexer. This is sufficient. Now, here again I take that same example of a 3 variable function. So, n equal to 3. So, how big a multiplexer I require? 2 to the power 2 to 1, that means 4 to 1, there are 4 inputs, 1 output and 2 select lines. Now, the question is, how do I apply these inputs to this multiplexer? Because in the earlier case there are 8 inputs, straight away we are applying the output column to there. So, the procedure that you follow is something like this. You see, it says connect n minus 1 variables to the select lines. There are 3 variables a, b, c. Let us say I connect a here and b here. 2 of the variables I connect to the select lines. C is still left, right, and we partition the truth table into groups of 2 rows. Like we first consider the first 2 rows. Let us look at the output and the variable that you have not yet assigned. We see that if C is 0, f is 0, if C is 1, f is 1. That means, f and C are the same. So, in the first input for 0 0 case, you see a b is 0 0, we directly connect the variable C to this first data input. We directly connect C here. Let us look at the second row, pair of rows now. Here you see that the outputs are 0 and 0 irrespective of the value of C, it is always 0. So, you apply directly a value 0 here in the second one, where a b is 0 1. Next 2 rows where a b is 1 0, you see irrespective of C the output is always 1 1 1. So, you apply a 1 here, and the last pair you see for 1 1 case D 3 will be selected. If C is 0, f is 1, if C is 1, f is 0. That means, the inverse of this. So, I will use a NOT gate and apply C bar to this. This will be my design. So, you see if I do this, then maximum I will be requiring one additional NOT gate to generate this C bar, and of course, this constant 0 1 I may have to apply and C I may have to apply. That is why it is mentioned apply the remaining variable, its complement C bar if required, and 0 or 1 at the data inputs, right. Let us take another example. This is a bigger example. I considered a 4 variable function. For a 4 variable function, I will be requiring 2 to the power 3 to 1 multiplexer, 8 to 1 multiplexer. So, this A, B, C, this we are applying here A, B and C, and we are applying the same rule. Consider the first 2 rows, you see output is 0 0 irrespective of D. Now, D is the last variable, A, B, C we have already applied, A, B, C is 0 0 0, D 0 is selected. So, we apply a constant 0 here. Next 2 rows, output is 1 and 1, always 1, you apply a constant 1 here. Next 2 rows, if D is 0, this is 1, D is 1, this is 0. So, apply D bar. Next 2 again 0 and 0, I apply 0. Next 2, if D is 0, F is 0, D is 1, F is 1, I apply D directly. Next 2, it is 1 and 1, I apply 1. Next 2 again, if it is 0 is 0, 1 is 1, I apply D. Next 2 again 0 1 1 0, I apply D bar. This will be my circuit. So, here we are inspecting the truth table and we are applying either 0 1, the last variable here D, or the complement of D bar to the input. So, I need a multiplexer, and just to generate D bar I need a NOT gate. That is all. So, you see using a multiplexer we can so conveniently design any arbitrary logic functions. So, we sometimes call this kind of multiplexer as generalized function generator because of this property. Let us look into one more thing, that we can implement arbitrary function using 2 to 1 multiplexers only. There is a principle called Shannon's decomposition theorem. This we shall be looking again later in some later lectures. So, what does Shannon decomposition theorem say? This says that if I have an n variable function, let us say f, the input variables are x1 to xn, we can decompose this function with respect to any of these variables. Let us say we are decomposing with respect to x1. So, if I decompose with x1, what will happen? This function can be written as x1 bar and this same function where x1 is replaced by 0, or x1 and the same function with this x1 replaced by 1. This is the Shannon's decomposition theorem. This you can do with respect to any of the variable, and in a compact form we write it as x1 bar f1 0. This is called f1 0, which means it is with respect to x1 we are setting x1 to 0, and f1 1 means this is x1 we are setting it to 1. Now, you see, if I do it in this way, you think in this way. Suppose I have a multiplexer here, this is a 2 to 1 multiplexer. I have 2 inputs, I have 1 output and I have a select line. Suppose I am connecting x1 to the select line, the output represents my function f. Now, if I connect this f1 0 here and if I connect f1 1 here, so does not this multiplexer implement this? If x1 is 0, then f1 0, if x1 is 1, then f1 1. So, every time you do this Shannon decomposition with respect to a particular variable, we can use a multiplexer to mimic that or to realize that. Okay? This is the basic idea. So, what I was saying, each application of Shannon decomposition theorem, as I said, is like a 2 to 1 multiplexer, where the variable is applied to the select inputs and this f1 0 and f1 1 are applied to the data inputs. Let us take a simple example. Consider a function like this, a 3 variable function a bar b, b c plus a c bar. Suppose we apply Shannon decomposition with respect to variable a. So, what is the Shannon decomposition? A bar and substitute a as 0. If a is 0, the last term will vanish. This a bar is 1, only b, b plus b c, b plus b c plus a and substitute a by 1, the first term will vanish, this will become 0, a by 1, this will become c bar, b c plus c bar. And if we apply minimization, b plus b c is nothing but b, b c plus c bar is nothing but b plus c bar. So, this decomposition you can express like this, you can have a mux where we have applied as select input a, the output implements f and you have the 2 inputs. In the first input I am just writing the function, you have this function b and the other input you have the function b plus c bar. Okay. Now, because in the first one you have only a single variable, I can directly apply b here, no problem, but for b plus c bar I may have to further do a decomposition. So, similarly b plus c bar, if you let us say decompose with respect to b, we get something like this, b plus c bar, b bar and substitute b as 0, it is only c bar, plus b, substitute b as 1, so 1 plus c bar is 1. So, here as if we are using another multiplexer, this we are decomposing with respect to b. So, the select line is b and the 2 inputs are c bar and 1, c bar and 1. So, you see, given any function, if you systematically carry out this decomposition with respect to the variables one after the other, you will be getting a network of 2 to 1 multiplexers. So, this is in fact a very general approach to implement any arbitrary switching function. This we shall be discussing later. There is a data structure called binary decision diagram. We shall see that this can be used in a systematic way to construct that kind of a data structure or representation. So, with this we come to the end of this lecture. Now, in this lecture we have basically considered multiplexers, its various kinds of designs, how to construct larger multiplexers using smaller ones, and also how we can design logic functions using multiplexers. Thank you.